Hey everyone, and welcome to This Explainer. Grab your hard hats because today we're treating our session like a live construction project. We aren't just memorizing commands here, we are building a miniature internet from the ground up. We're taking a deep dive into Midterm Activity 5, focusing on BGP implementation and OSPF redistribution across a 6-router topology. If you've ever wondered how local, isolated networks actually manage to speak to the massive global backbone of the internet, well, you're exactly in the right place. Let's get this build started.
Okay, let's dive into this blueprint and look at our core objectives. We're outlining a completely functional architecture here. First up, we need to establish our basic router settings. Second, we're tasked with implementing BGP, Border Gateway Protocol, across 6 routers arranged in a really specific core and edge design. Third, we'll configure OSPF on our edge routers and perform mutual redistribution into BGP. And finally, our ultimate proof of concept, verifying full connectivity by pinging all end-user PCs across the network. We're not just configuring devices today, we're literally building bridges.
To keep us on track with all getting lost in the code, here's our flight plan for the build. 6 logical, bite-sized phases. We'll start with the topology blueprint, lay down our basic foundation, configure OSPF on the edge, scale it up with BGP, bridge the protocols with mutual redistribution, and finally, verify the whole shebang. All right, Phase 1. The 6-router topology blueprint. Because, as any good engineer knows, every great network starts with a solid architectural foundation. Now, what's really interesting about this layout is the clear division of labor. We're dealing with 2 completely distinct domains. Right in the center, we have our core routers, R1, R2, and R3. They're connected in a full mesh triangle. Think of this as the heavy-duty highway system of our network. Then, on the outskirts, we have our edge routers, R4, R5, and R6. R4 connects to R1, R5 to R2, and R6 to R3. Most importantly, these edge routers are the ones physically connecting to our end devices, PC1, PC2, and PC3. Our entire job is to make sure a packet from PC1 can navigate through its edge router, safely cross that core triangle, and arrive at PC2 or PC3.
Of course, to navigate that heavy-duty highway, our data packets need a literal map. This IP addressing plan cleanly maps out the networks using a standard /24 subnet mask per link. For example, the link between router 1 and router 2 uses the 10.0.12.0 network. R to R3 uses 10.0.23.0. It's a super intuitive naming convention that makes troubleshooting so much easier later on. And down at the bottom, we see our local area networks for the PCs using that very familiar 192.16.8 block. This addressing plan is absolutely the bedrock of our routing.
Moving right into Phase 2, laying the basic foundation. Before we can get to the advanced routing, we've got to prep the hardware. This step is basically the digital equivalent of pouring the concrete and locking the doors. For all 6 routers, we execute a brisk series of standard commands. We jump in, set our host names, R1 through R6, and then lock it all down. We're setting the enable secret password to Cisco123, securing the console and VTY lines with Cisco, and dropping in a solid message of the day banner warning off unauthorized access. It's just standard best practice to set the stage for a professional build. With the doors locked, let's power up the links. Looking at this snippet for router 1, you can see how meticulously we follow that IP plan from earlier. We jump into interface Gigabit Ethernet 0/0, apply the IP address 10.0.12.1 with a standard Class C subnet mask, and hit it with that crucial no shutdown command to bring the interface to life. We repeat this across interfaces G0/1 and G0/2 on R1, and then carry out that exact same methodical process across all the routers. Meticulous data entry right here absolutely prevents massive headaches later. Links are up and addressed. Let's hit Phase 3. Configuring OSPF on our edge routers. Time to establish local communication. OSPF, or Open Shortest Path First, is basically going to act as our local neighborhood watch. We configure this specifically on our edge routers. Let's take R4, for example. We initialize the process with router OSPF 1. Then we use the network command to advertise the directly connected networks. We toss both the WAN link, the one pointing toward the core, and the local LAN where PC1 lives straight into Area 0. This ensures local devices like PC1 can reliably reach their immediate gateway router. Neighborhoods are good to go. Phase 4. Implementing BGP across systems. It is time to build the global steel framework that ties these isolated networks together. So the crucial point here is understanding how Border Gateway Protocol actually views the world.
BGP routes between entire autonomous systems, or AS numbers. Notice how our numbers are assigned here. Our core triangle, R1, 2, and 3, they all share one unified autonomous system, AS 65,000. But look at the edge routers. They're completely separated. R4 is AS 65,100, R5 is 65,200, and R6 is 65,300. This deliberate separation makes this a true BGP exercise. We're basically mimicking how different ISPs connect to a massive internet backbone.
Bringing this to the command line, on router 1, we kick off router BGP 65,000. When R1 points to R2 and R3 using remote as 65,000, it forms an internal BGP, or IBGP relationship because those numbers match. But when R1 points outward to its edge router R4 using remote as 65,100, that forms an external BGP, or eBGP relationship. We repeat this logic for our edge routers. On R4, we start process 65,100 and point back to R1 at 65,000. Just like that, we've built routing bridges from the isolated edges straight into the central core.
OSPF is running locally, BGP is running globally. Phase 5, Mutual OSPF BGP Redistribution. This right here is the absolute crux of our entire build.
Right now, we've got a major language barrier. Our edge routers know the local lands via OSPF, but the core routers only speak BGP. We have to provide a real-time translator. Enter route redistribution. By definition, this is the process of translating and sharing routing info between different protocols. Without it, PC1's local network is just a secret known only to OSPF. We need to inject that secret straight into the global BGP conversation. And this brilliantly illustrates that redistribution is a two-way street. First, under the BGP config on R4, we literally type redistribute OSPF1. That grabs the local PC1 network and shoves it into the BGP core. But traffic needs to know how to get back, so we flip it. Under the OSPF configuration on R4, we type redistribute BGP 651000 subnets. This grabs the massive global routing table from the core and translates it all the way down to the local LAN. Setting up this mutual redistribution guarantees data flows fluently in both directions.
The coding is done, the bridges are built, the translators are working. Phase 6, network verification and testing. Time to inspect our masterpiece. You can never just assume a network works because the commands didn't throw an error. We have to verify. We hit Show IP BGP Summary to make sure our BGP neighbors are actually established, meaning we see numeric values under the prefix column, not just stuck in active or idle. We use Show IP OSPF Neighbor to confirm local adjacencies. And finally, Show IP Route gives us the ultimate truth, the routing table itself. We want to see OSPF routes, BGP routes, and most importantly, those beautifully populated external redistributed routes.
Let's move to the ultimate payoff, successful pings. From the command prompt of PC1, sitting way out on the edge behind R4, we ping PC2 at 192.168.2.10 and PC3 at 3.10. Seeing those replies come back is huge. It means our packet successfully left the OSPF network, got redistributed into the BGP core, crossed that entire full mesh, was redistributed back into a totally different OSPF network, and then the reply made the exact same journey in reverse. It proves the architecture works flawlessly.
So you've just successfully built a fully functioning multi-protocol network. But I want you to think about this for a second. Today, we used BGP and mutual redistribution to get PC1 talking to PC3 across just 6 routers and 3 autonomous systems. The internet you're using to watch this explainer right now uses these exact same underlying mechanisms. If 6 routers can bridge 3 distinct systems in a lab today, how might these exact same redistribution principles scale to connect hundreds of thousands of systems across the global internet tomorrow? The rules you applied today are literally the rules that run the world. Thanks for building with me, and I'll catch you in the next one.